So welcome students. In this video we are going to talk about something a little different. So from now on, for the next few lectures, what we are going to do is we are going to talk about some equations, right? So up till now we talked about systems. We looked at whether there is existence, uniqueness, and what are the properties which you can expect out of the solutions, right? Now we are going to look at some system which is given by this. So consider the system, the equation. Consider the equation P naught of x y double prime, x is a variable here, right, plus P1 of x y prime plus P2 of x y. Okay, so this is a system. Let's say this is equals to 0 given. Again here what we are doing is we are going to assume that P0, P1 and P2 are smooth. I mean, most of the times continuity is enough, but let's just say smooth. Smooth means it is at least C1. Okay, continuously differentiable, and that is fine. Yeah, let's just take it like this. Now you see, the thing is, for let me just give you an exact idea of what we are trying to do here. Okay, see, we want to solve this problem. Yes. Now, why this problem? See, so let's put it as a small remark. Now, for this problem, let's say P0 x, P1 x, P2 x, these are all constant functions. So, if P0, P1 and P2 are constants, constants, let's say, then we can solve the problem, right? One can explicitly solve the problem, right? You remember e power mx kind of thing, right? Solve the problem, solve the equation. Yeah, and what about the inhomogeneous part? Of course, if you have the solution of the homogeneous part, you know that you can use Duhamel's principle to find out the solution of the inhomogeneous part. So that is there. Yeah, so we can actually solve this problem. But the thing is, what happens if you have a variable coefficient? So P0, P1, P2 are like smooth C1 functions. Now in this case, you see, so this is A, this is B. If P0, P1 and P2 are smooth, okay, then Picard gives us Picard's theorem. So how can you apply Picard here? Picard theorem, you remember, you can actually reduce it to a system, right? And that system and this equation are basically equivalent. For that system, given initial data, you know that there is a existence and there is a uniqueness. So basically, this equation has a unique solution. Okay. So then Picard's theorem guarantees unique existence, right? So basically, we know that there is a solution provided the coefficients are smooth enough. Okay. Now the thing is this: what we want to do is this: is it possible to explicitly solve? See, finding giving an existence theorem is fine, but the thing is, can you solve this problem? Yes. And as you have seen, the variable coefficient equation can be very, very tricky. Okay, even for some simple coefficients. So basically, for simple functions also, if you are just assuming it, then also it becomes very difficult. Okay, but there are some instances where this is very easy to solve. How to do that? So here comes the idea of exactness. So what we are trying to do here is this. See, the thing is, let's call this as 1. The equation 1 is exact if P0 of x y double prime plus P1 of x y prime plus P2 of x y, this expression can be written as P of x y prime plus Q of x y, the prime of that. Clear? Okay, where P and Q are continuous, are differentiable functions, are continuously differentiable. So C1 functions. Why? You see, I want this expression, I want to write it like this. You understand? and so of course I am taking the derivative of that function. So basically I need p and q to be at least c1, right? So you see, if this is the case, then we say the function is exact. So basically the thing is, if you can find a p and a q c1 function such that you can write this expression like this, then we call it a exact equation. Here now you see the necessary condition, and also the necessary condition is this. When can you write it? Necessary condition. So when can we write it? You see, if this is the case, then if you break it up, it becomes p prime y double prime plus p y double prime plus p prime y prime plus q prime y prime plus, again what am I doing, q prime y plus q y prime. Is it okay? So that will be equals to p naught y double prime. I am not writing x all the time, it is assumed, right? So we are just avoiding it, plus p2y. Here now you see, if you compute this thing, essentially what is happening is this. Now hence one have that see this equation, if you look at it properly, it is what? P minus p naught y double prime plus p prime, right? P prime, this equation, minus p1 y prime, okay, plus q, plus q is there, plus q y prime, okay, and then plus q prime minus p2 y equals to 0. This is okay. Now you see, I want my this expression to be equals to this, yes, and this should hold for all y. It's not for a fixed solution y, right? This should hold for all y. Is this okay? I hope this is clear. See, we are not trying to solve the problem. Essentially what we are doing is we are trying to say that this expression is equals to this expression, and for any y, essentially, it doesn't really matter what y is. So basically, let's say, and at least such a y such that y double prime exists and it is continuous, right? So basically we are looking for a y for this should hold for all y in C2. Is this okay? C2 of I, whatever the interval we are looking for in that interval. Yes. So you see, now take y of x to be, let's say, x, then y prime is equals to 1 and y double prime, maybe I can take y to be 1. Let's take y to be 1. Let's take y to be 1 first of all. Let's do that. Y to be 1. So if you do that, then you see y double prime is 0, y prime is 0. So basically q prime has to be p2. Okay. So you get this expression, q prime equals to p2. That will imply what? So you know what is q. So q is such that q prime equals to p2. Okay. Now also if you take, let's say, yx to be x, okay, and q prime equals to p2, this is already given, right? So I will see, I mean, the choice of p and q is on us. So basically if we choose q prime equals to p2 and yx equals to x, then also this expression, the star should hold. So then what happens is this: if y is x, y prime is basically 1, right, and y double prime is basically 0. So this part is gone. So in that case, p prime will be p1 minus q. And similarly, you can also show that p has to be equals to p0. Okay. choose a, nice enough function such that y double prime is equals to 1, this is 0, this is 0. Okay, you can of course do that, and then you can show that p equals to p naught. Is this okay? Yeah. Once you do that, then what happens is you are going to get, I did some mistake somewhere. Yes, one second. Y prime, p prime minus p1. So p1 is p prime plus q, no? P1 is p prime plus q. No, it's okay. Yeah. Okay. So now you see, therefore, these equations imply, this implies. What does it imply? You see, p prime is p1 minus q, p equals to p naught, right? So p naught prime is p1 minus q. That's what you are going to get, right? And then q prime is p2. So basically, if you put all of this together, see what do we have? Let us write it here. Huh? This implies no. Let us write it here. Otherwise, we will get confused. So what do we have? P naught is p. P1 is p prime plus q, and we have another one, right? P2 is q prime. P2 is q prime. So if you put it together, therefore, if you put all of this together, it becomes p naught double prime of x minus p1 prime of x plus p2 of x is 0. This is okay? Huh? So therefore the differential equation 1 is exact if and only if, right, p naught double prime of x minus p1 prime of x plus p2 of x is 0. Is this okay? Yes? Okay. So this is the expression, right? Now the thing is this, see, if this is exact, what is so special about it? Let's say if you can show something is an exact, what is so special about it? So let's look at this expression: x double prime y, x square y double prime plus xy prime minus y equals to x to the power 4, and x is positive. Clear? I want to solve this problem. Yes. Now, by the looks of it, of course, this is in Cauchy-Euler form, right? So it can be solved. It is not a very it's not like an unsolvable problem. It can be done, but it is going to be very messy. I will show you a very easy way of doing it. So what we are going to do is this. See, let's say here p naught of x is x square, p1 of x is x, p2 of x is minus 1. Okay. So if you take p naught double prime minus p1 prime plus p2, if you take that, that is going to be 0. Okay, that will imply that, let's call it 2 is exact. Okay, now the thing is, it is exact. So what? Okay, what do we get? See, what you can do is essentially, you can have a p1 and p2. See, you can have a p and q such that this, you can write it like this, right? You can have a p and q. And what is p and q? P is p naught. And what is q? Q is q prime equals to p2 essentially. Okay, so therefore we can write it as this. P is q naught, right? So you see, p is p naught. Okay, so I can write it as py prime plus qy whole prime. So p naught is here x square y prime. Okay, and then I can write it as plus qy whole prime. Okay, what is q? Q is nothing but q prime is p2. What is p2 here? P2 is minus 1. Okay, so p2 prime is minus x. Okay, so xy. This is what we are going to get, right? The derivative of this. Yeah, this is equals to x to the power 4. We will get it like this. Is this okay? You understood what I am trying to say? See, here, if it's exact, you can write it like this. So basically, you see here, p naught is p, and what is q? P2 is q prime. right? What is P2? P2 is minus 1. So Q prime is minus 1. So Q has to be minus x. So it is this. Huh? So this is fine. Now you see, if this is the case, then we can write it as x double prime y prime minus xy equals to x power 5 by 5 plus some constant c. Very simple. Okay, and then we can of course solve this. This is just a first order equation, right? It's very easy to solve. So please solve this and see that this is the solution which you are going to. So this is the first order equation, first order differential equation. Yeah, you can use integrating factor here, very easy. If you are integral x, so basically you multiply it and after that you solve it, and this is the solution which you are going to get. X to the power 4 by 15 plus c1 by x plus c2 x. Is this okay? This is the solution. So you understood how the problems are solved, why exactness is so important. Okay, now let's look at an expression. What happens if the equation is not exact? So if the equation 1 is not exact, what happens then? Okay, so can you guess anything what is happening? What we will do is this. See, then we seek an integrating factor, IF, integrating factor. Okay, so what is the integrating factor? It's a positive function which you multiply with your original equation, and that will actually give you a exact equation. Okay, integrating factor, let's say z of x, that makes 1 exact, So you understood the idea. The idea is this. See, 1 is not exact, but can we make it exact? So basically what we are doing is we are assuming, we don't know whether such thing happens or not. What we are doing is we are assuming that, let's say there is a z, such that when you multiply the equation with z, what happens? Then the equation becomes this, right? P naught of z y double prime plus P1 of z y prime plus P2 of z y equals to 0. Okay, now let's call this thing as 3. Now 3 is exact if when? What is the expression? See, this is, let's say this is nothing but Q naught. This is Q1. This is Q2. Right? So when is it exact? If P naught Z double prime, Q naught double prime, you see? This is this expression. Minus P1 of Z prime plus P2 of Z, this is going to be 0. Yeah, that's your expression. Okay, this will actually give you, so I will write this equation as P naught Q naught, right? So I will write it as Q naught of x Z double prime plus Q1 of x Z prime plus Q2 of x Z equals to 0. Okay, where what is Q naught of x? Q naught of x is nothing but this expression, P naught of x Q1 of x is nothing but 2 P naught of x prime minus P1 of x, and Q2 of x is nothing but P naught double prime of x minus P1 prime of x plus P2 of x. Is this okay? Yeah, you can just solve it. So please check this part. So you can just solve this problem and just write it like this. Yeah. Okay. Now you see this expression. Let's just call it 4. Okay. So if you think about it, see that if you write this properly, so this also you please check this part. Check. 4 is equivalent to this system. What is the system? Let's just call U1 prime, U2 prime, which is nothing but 0. Oh, sorry, I should uh, no, I should I don't know which one I wrote here. Okay, this one. Okay, so you see this one, if you write it in terms of a system, it will look like this, no? U1 prime, U2 prime is 0, 1 by P naught of X, U1, U2. Okay, I'm just writing. You see, this is not 4, huh? This is not 4, this is 1. 1 is equivalent to the system, okay? And then minus P2 of X and P naught prime of X minus P1 of X by P naught of X. Okay, please check this part. How do you check it? You see, first of all, what is from here, what is U1 prime? It is nothing but 0 times U1, 1 by P naught times U2. Clear? And the other part is U2 prime is minus P2 times U1 plus P naught prime minus P1 by P naught times U2, right? So you put this expression here, and after that calculation you are going to get it. It's very easy, yeah. So please check this part, huh? This is for you to check. Also, so if this is the case, so you see, you can write it as, let's say, U1 prime, U2 prime equals to some function A x times U1, U2. Okay. So you remember we talked about the adjoint equation. What is the adjoint equation? This is the original equation. So adjoint will be, let's say this is x equals to a okay, at times x. If this is the equation, the adjoint will be minus a transpose, right? Okay. So you see, if this is the equation, okay, this also I want you to check. Then its adjoint equation, adjoint system is V1 prime, V2 prime is 0, P2 of X, okay, minus 1 by P naught of X minus A transpose, right? So exactly the same thing, minus A transpose, that is P naught prime of X minus P1 of X by P naught of X, and then V1 and V2. Is this okay? This is what we are going to get. Now if you write this, you see, this is basically V1 prime is nothing but P2 of X V2, and V2 prime is nothing but minus 1 by P naught of X V1 minus P naught prime of X minus P1 of X by P naught of X V2. This is what you are getting. Now if you put everything together, okay, so this expression, if you put it here, therefore what do you get? You are going to get P naught of X, okay, V2 double prime plus P naught prime of X V2 prime equals to minus P2 of X V2 plus P naught double prime of X minus P1 prime of X V2, sorry about it, V2, okay, minus, so this is a little calculation, but we have to go through it, so please bear with me here, minus P1 of X V2 prime. I hope this is the calculation is correct, so please check this part. If you are not convinced, please check the calculation. Yes, I hope this is clear. So if you put it together, what happens? This is nothing but P naught of X V2 double prime plus 2 P naught prime of X minus P1 of X V2 prime plus P naught double prime of X minus P1 prime of X plus P2 of X V2 is 0. Yes. Now you see this equation, this equation, this equation and this equation are basically same. You see, these and these are basically same equations, right? Okay, so what is happening is this, that when you multiply a z and the basically that equation becomes a exact equation, that equation is nothing but the adjoint of the original system. You understand the original equation. So if you are given an equation, so basically what it means is this: if you are given an equation, right, and then you multiply it with the indicating factor, and if this equation is, after multiplying it, if the resulting equation is exact, then that equation is nothing but the adjoint of the original equation. That's what it is saying. Okay, right. Now let's look at a definition. We'll put a definition here. Okay, you see, the thing is, 1 is said to be okay, self-adjoint. So basically when it is the same as, the equation is same as its adjoint. Okay, so if the equation and its adjoint equation are same. I hope this is clear. Okay, you see, it may happen that the equation and the adjoints are basically same, right? In that case, we call it a self-adjoint equation. What is the relation? Therefore, 1 is self-adjoint if, what is the relation here? If P naught of x equals to Q naught of x, okay, and the other expressions, P1 of x has to be equals to Q1 of x, and P2 of x equals to Q2 of x. Is this okay? See, adjoint equation, this is the adjoint equation, right? The original equation is this. So basically it is P naught is Q naught, P1 is Q1 and P2 is Q2. That has to be the case. Okay. See, P naught and Q naught are already same. If this is equals to, if Q1 is equals to P1, then basically that will say that P1 equals to Q1, then it says that P naught prime has to be P1, right? That's what it is saying. So therefore, which implies that P naught prime of x has to be equals to P1 of x. Okay, so that is the relation which the equation has to satisfy for this to become a self-adjoint equation. Okay, so let's put it. Therefore, 1 is self-adjoint if, okay, you see, this is 1, right? P1 of x y prime plus P2 of x y equals to 0. Now you see, if it is self-adjoint, P naught prime is P1, so it is, you can write it as this: P naught of x y prime whole prime plus P2 of x y equals to 0. This is a self-adjoint form. Okay, please remember that it is extremely important. You must remember this thing. We are going to work with it a lot. This is the self-adjoint form of 1. Is this clear? Okay, so this is the form. Okay, so you see, hence what did we find? Let's just understand that. So you see, we multiplied let's say sigma x with 1. We multiplied sigma x with 1. Okay, and if it is self-adjoint, what is the expression? See, 1 is given, right? Yes, and now I want 1 to be self-adjoint. Okay, what is the expression? If P naught prime is P1. Okay, so 1 is given by this equation. I multiplied by sigma x, and then if it is self-adjoint, what happens? That P naught prime is P1. So in that case, it will look like this. that sigma x p1 of x should be p naught prime, right? So in this case p naught is sigma x p naught x. The derivative of that is equals to sigma x p1. Is this okay? This is same as nothing but sigma x p naught of x, the derivative of that, by sigma x p naught of x. Let us do it this way. So then that will give you p1 of x by p naught of x, right? So that will give us, one second, that will give us sigma x is nothing but, you see, if you integrate both sides, what is going to happen? It is be 1 by p naught of x exponential integral over x p1 of s p naught of s ds. This is what you are going to get, right? So what happens is, you see, if this is the integrating factor, which will actually, when you multiply it with your equation, will actually make 1 exact. So hence sigma given above turns an equation, turns 1 into its self-adjoint form. Adjoint form. So I hope you understood what I am trying to say. See, what I am trying to say is this: if you are given 1 and if you want to put it in a self-adjoint form, what you do is you multiply it by sigma. What is sigma? Sigma is essentially this. Okay, so if you multiply it with this equation, it actually becomes its self-adjoint form. Okay, so that is how you transform an equation in a self-adjoint form. Okay, now the next part is very, very, very important. Okay, so let me put it very, very, very important. Okay, yeah, please understand what is happening, because we are going to use it to solve many a problem. Okay, fine. So you see, the thing is, one second, where did I put it? Okay, let me write it this way. See, sigma naught of x, let's say sigma, sorry, not sigma naught, sigma of x is such that it makes it self-adjoint, right? So if you take that sigma, so sigma is an integrating factor which makes the equation self-adjoint, times p naught of x y double prime plus sigma 1 of x, sorry, what am I writing? p1 of x y prime plus sigma of x p naught of x y equals to 0. This equation is self-adjoint. Let me write it this way: self-adjoint. Clear? Okay. So I am going to deduce something, yeah, and I am using a little facts here. So please understand this. See this equation. So let's call this as star. Star is self-adjoint. Yes, and its solutions, okay, are also its integrating factors. Integrating factors, right? This is quite evident. You see, if you solve this is the self-adjoint equation, right? So if you solve this equation, the solutions, that will also be an integrating factor, right? Okay, so but since star is what? Star is essentially 1 multiplied by sigma x. Okay, so but since star is 1 multiplied by sigma x, what does that imply? That will imply, hence that will imply that the solutions of star okay, is same one second, by mistake I am writing something. the solutions are indicating factor, that is fine, and star is nothing but sigma x times 1, right? That's what it is. Yeah, so you see, okay, so hence sigma x times the solution of 6.1, sorry, the 1, sigma x times the solution of 1 okay, are the solutions of the solutions of star, okay, which are also the integrating factors, okay, because solutions are integrating factors. Okay, so sigma x times the solution of 1 are the solutions of star. Okay, so but since the integrating factor of 1, okay, are solutions of the adjoint equation okay, then what do you have is C, we will write, how do I put it, maybe one second, okay, so you see, where is that equation gone? I don't know. There are so many equations, it gets confusing. Okay, 4. Okay, so you see, this equation is nothing but the equation multiplied by the integrating factor, right? So and the solution is given by z. Okay, so what happens is, then z of x can be written as sigma x times what is it, y of x, no? Okay, fine, yeah, and hence zx by y of x is nothing but sigma x, which is again given by 1 by p naught of x exponential integral p1 of s by p naught of s ds. Okay, is this okay? Sigma x is given by this, right? So I'm just writing it this way. Yeah, okay, fine. So this is basically the thing which we need, huh? So essentially this is the expression which we need. Yeah, now the thing is this, I just wanted to reduce this part, that zx can be written as sigma x times yx, where sigma x is given by this. That's the important part. Okay, now why it is important, let me just do this part, and then we are going to finish this video. So with an example, why this is important. Example, this makes our life very easy. Why? Because let's look at this problem, xy double prime plus 2y prime plus a square xy equals to 0. Okay, let's say x is positive here, okay, x is positive here. So this is not exact. Why it is not exact? Let's say the equation is not exact. Why it is not exact? Because if you look at p naught double prime minus p1 prime plus p2, this is 0, this is 0, so ultimately this is just an a square x, which is definitely positive. Okay, and what about its adjoint? Its adjoint equation is, what is the adjoint equation? It is given by x z double prime, okay, minus 2 z prime plus a square xz. That's the adjoint equation. See, this is the adjoint equation. Where is it? I wrote it somewhere, no? Where is the adjoint equation? This one, the 4. 4 is the adjoint equation. Okay, so you just write that part. So given an equation like this, first of all write down the adjoint. So that is, what is the adjoint equation? It is given by x z double prime plus a square z equals to 0. Here x is positive, so that will imply that z double prime plus a square z equals to 0. Yes, this is the adjoint equation, right? Now the general solution of this adjoint equation, what is the general solution? That is given by c1 times cosine ax plus c2 times sine ax. That is your z of x, right? Okay, and what is sigma x? Sorry, sigma x. So what is sigma x? It is 1 by p naught, right, which is x, and then exponential integral p1 to by p naught t dt. So if you calculate it, this is log, right? Log square. So basically it is x square by x, which is x. Okay, so hence what is the solution of our original problem y of x? It is nothing but zx times sigma x, right? Sorry, zx by sigma x, zx by sigma x. I hope this is correct. Okay, fine. It is c1 times cosine ax by x plus c2 times sine ax by x. Is this okay? This is how you solve the problem.